Okay. It is almost 5:10, so we can go ahead and get started. Hi, everyone. I hope you're having a good evening. Our Stat 100 final is on Monday, so this will be a great review. Honestly, if you feel comfortable after this, you should be good to go. I am going to just kind of go through this practice exam that is in your notebooks. It's the spring 2012. It's a really old one. And I guess I'll try and go through all of the questions. If we don't go through all of them, I think I can stay on afterwards and ask more questions. But let's go ahead and start. So I wanted to give all of you just a heads up about the final on Monday. It is on Compass like the other exams, so you obviously won't have to show your work or anything. It's going to be all multiple choice, which is slightly different than the previous exams. We had a lot of fill in the blank questions before. But the final is all multiple choice, and it is very similar to this practice final, which is why I'm going to do this one. So the exam goes relatively in order. We start with kind of the exam one stuff and then end with hypothesis testing. But it's not exactly in order. Like here you can see questions 1 through 8 are about histograms and not experimental design. So people ask me that a lot. Does it go in order? Okay, let's go. We have a histogram here, and it says we're looking at the age at death of a large population. And it says the height of each block is given in parentheses. We want to assume an even distribution throughout the final. So these questions are just asking about the histogram. What I would do in this scenario is kind of figure out, okay, what are the percentages? Because I'm guessing it's going to ask me about that. So to find the percentage for each block, we're just going to take the width times the height. So that's going to be the area of each block. So area is width times height. And so like for the first one, the width is from 0 to 20, so it's 20, and the height is 0.25. So that gives me 5%. So that means that 5% of people died between the ages of 0 and 20. And then I can go ahead and fill in the rest of these. Like the next one, I have 20 to 40 is my width. So my width is 20, my height is 0.5, so this is 10%. And then this one is also 10%. This one is 25%. This one's 25% as well. And then we have 15 and 10%. So remember, the area of the total histogram has to be 100%. And now I can answer these questions a little bit easier. One says, what percent of the population died in the 70 to 80 interval? And we saw that was 25. Width is 10. Height is 1.5. Or sorry, wait, 70 to 80. Width is 10, height is 2.5. And then what is the median? So remember, the median is the 50th percentile. And here I didn't give you guys all of the different ages. If we did that, we could list the numbers in order from smallest to biggest and then pick the middle number. But instead we have the percentages, because I'm going to use the idea that the median is the 50th percentile and find the point where there's half the data below that point and half the data above it. So if I look here, I'm just going to start at the end point. So starting with 20, that's the 5th percentile. There's 5% of the data to the left. Let's check 40. Right at 40, there is 10 plus 5. So 40 is the 15th percentile. And then what else? 50. That's 10 plus 10 plus 5. So that's the 25th percentile. We're getting closer. And then right at 70, that's the point where I have 50% of the data to the left and 50% of the data to the right. So that's going to be my median. And let's see, next question says, how does the median compare to the average? And for the median and average, again, we don't know. We know what the median is here, but I can't figure out what the average is because we didn't give you all of the data. But I can say this histogram has a nice long left-hand tail. It doesn't look like the normal curve. If anything, it's a little bit skewed. And so the median, remember, is the 50th percentile, and then the average is takes into account all of the data, and it's the mean. So if there's a long left-hand tail, then these lower numbers are going to affect the average. The average is affected by the extreme values. So the average is probably going to be smaller than the median in this case. Average is less than the median. And that means, if I'm looking at this question, it says the median, how does the median compare to the average? So I'm actually going to say the median is greater than the average. And then somebody said, can you go over how we would calculate the average? So here we can't actually calculate the average. We don't have the data, but I know because of the shape of the histogram, the average is affected by the extreme values. So if the average is really, if there's a lot of low extreme values, that will drag the average down. If we had a histogram that was shaped like this, kind of the opposite, then we have most of the data down here by 0, and then a few higher outliers closer to 100. So here, those high values would be dragging the average to be greater than the median. Okay, and I saw someone said the volume's a little low. I just turned it up on my end. Hopefully that helps. All right, 25th percentile. Percentile, remember, is the area to the left of whatever that value is. So 25th percentile in this case would be 50, because right at 50, I have 10 plus 10 plus 5. I have 25% of the data to the left. And then next question says the percent of the population who died at 75 years is closest to what? So this is interesting, because we know that 25% of the population died between 70 and 80 years, but right exactly at 75 is like this part of the histogram. It's this little sliver of that block. So that's 75. And if I want to find the area of that little sliver, it would be, again, what we said before, the width times the height, but the width is just going to be 1 here because we're just looking at 75. So the width is going to be 1, and then the height is 2.5. So this should be 2.5%, which is E. So that's always kind of a tricky question. If I ask something else like what percent of the population died when they were 2, that would be right here. That would be this little sliver. Here is 2, and the width would be 1 in this case, and then the height would be 0.25. So that would be 0.25%. So up here it said we want to assume an even distribution throughout the interval. So we're assuming an even amount of people died at each age. Somebody asked, can you also do 25% divided by 10? Yes, for sure. You can take the percentage that we found for each block and then divide that by the length of the interval to get it as well. That's another way to do it. All right, let's see. Next one says, if everyone lived 1 more year, what would happen to the average? So the average is sensitive to any changes. If everyone lived 1 more year, the average would increase by 1 year. And same with the median. It doesn't ask about the median, but if it did, the median would increase by 1 year as well. The SD is the spread of the data, so I like to look at the range. And here the range is 0 to 100. And if we increase everybody's age by 1 year, then the range would be 1 to 101, right? So the range is actually staying the same. It's still 100. We're just kind of shifting it over. So this one should be say the same. And then last question for the histogram, it says if you knew the average in the SDs, would it be appropriate to use the normal approximation? Here I would say no, because our histogram doesn't look like the normal curve. So what the normal approximation does is says, instead of this histogram, I can approximate it with the normal curve. And that here, that wouldn't work very well because it has the long left-hand tail. So I'm gonna say no, yeah. C is the only one that says no. Let's see, somebody asked, when does the SD not stay the same? That's a good question. So it would be whenever the range changes. So say in this case, I took the oldest person and added 50 years to their age, then my range would be from 0 to 150. So in that case, the SD would increase. Somebody said the SD would change if we were multiplying. Yeah, so if I took everyone's age and multiplied it by 2, then my range would go from 0 times 2, which is 0, to 100 times 2, which is 200. So my SD would increase as well. All right, any more questions on the histogram? Okay, I think that's pretty much a lot of what we talked about histograms. And I'll tell you guys this, that the final is not very specific, so it's kind of a general overview of the whole class. So you'll notice there we can't ask every single question about everything we've ever covered, but just kind of the general concepts from each unit. Is there more practice on these histograms? Yeah, you can do the homework as practice. All the long kappa problems you can do again with different numbers. And then all of the exam ones have histogram questions on them. And then the other practice finals have histogram questions as well too. Would you say the final is easier than the other tests? I feel like I'm a terrible person to ask that question. I would say it's probably about the same in terms of difficulty. Usually, if I'm just looking at data from the past, the average on the final is about an 83, which is pretty consistent with the other exams. This semester, honestly, it might be a little bit higher because it's open book. All right, the next few questions I'm gonna go through really quickly because I feel like you guys know how to do this. We're going to add up all the numbers, divide by 4, and my average in this case should be 2, right? And then the median, to find the median, just don't forget that you do have to list the numbers in order from smallest to biggest. So I would start with -2, 0, 2, and 8, and then it would be the middle number, which is 1. So one of the things, just don't forget to list them in order. That's a common mistake. The deviations, you're just going to take every single number on the list and subtract the average. So subtract 2. So 2 minus 2 is 0. -2 minus 2 is -4. And then etc. So we should get E. And then if we wanted to find the standard deviation, I would go ahead and take these deviations. So to find the standard deviation, this is step 1, this is step 2, and then you can see chapter 4 for the other steps, but step 3 would be to square the deviations. Square the deviations. That would be step 3. Step 4 would be to take the average of step 3 of the squared deviations, and then step 5 would be to square root. So this doesn't ask for the standard deviation, but I'll give you guys a hint. The one on the actual final does ask for it. And then question 12, this says a list has 6 numbers. We have 5 deviations from the average. It should say what is the 6th one, right? 6th. And this should be, so how do we figure this out? Because we don't have, it just says a list has 6 numbers, but I don't know what's on the list, so I can't find the average and subtract that. But what I can do is think about the properties of deviations. And there was one thing that always was true about them, and it's that they sum to 0. The deviations do. So I know if there's 6 numbers, if I add up all those deviations, I should get 0. So right now I know 5 of them are 1 plus 2 plus 3 plus 4 plus 5 plus, and then the 6th one, I'll just call it x, has to equal 0. And so the missing one must be, if I add all these up, it should be negative 15. It has to be negative, so I know it has to be one of the negative answers, because all those are positive. But yeah, this is when I get questions a lot on, just because people are like, how do I figure this out? But yeah, remember the deviations sum to 0. All right. I don't see any more questions, so we'll keep on going. Next, it looks like these are more experimental design questions. And I am going to start with the first one. It says a study published in the journal Autism Research found that older mothers are more likely to have autistic children than younger mothers. This was a study that examined birth records, and it says the maternal age for one group was 30, the maternal age for the other group was 27, and they found, here are the findings, mothers over 40 were 77% more likely to have given birth to an autistic child than mothers under 25 were. So they saw this difference. It seems pretty big. But reading this, I see no mention of random assignment. This is about children and giving birth, so we can't randomly assign mothers to do a lot of things. So here, this is definitely an observational study. So I would beware of the conclusion. Maybe there's this correlation between being an older mother and having an autistic child, but we can't say for sure that there's a causal relationship. So I'm going to keep that in mind. I guess number 14, which statement is best? This right here, I can't say because the study wasn't random. So I'm going to get rid of that one. What else? This study shows maternal age is associated with autism. It doesn't show whether or not it causes it. That sounds good to me. This definitely does not cause. I don't like that because it could, but we just don't know. So definitely, statistics is never having to say you're certain. So I'm not going to pick that one. But with this chapter on experimental design, remember the randomized controlled experiments are best. And if we have a randomized controlled experiment, we can look at the outcome and say, all right, there were no confounders in this study. As long as it was done properly, the conclusion is probably going to be correct. What else do we have here? These are the classic questions of identifying confounders and causal links or neither. So I am going to use, if you guys think way back to the beginning of the class, I showed you how I like to do these problems with the diagrams. So I'm just going to go ahead and do that here. Let's see. Heredity. Mothers who have autistic tendencies themselves are both more likely to have autistic kids and more likely to be older when they give birth. All right, let's check this out. So if I was going to write my diagram, I'm going to put basically the treatment, the thing that they give us, and the response. So in this case, the treatment is so this study is trying to say older moms are more likely to have autistic kids. So the treatments I'm going to say is being an old mom. And then the thing we're looking at is heredity. And then the response is autistic kids. So always good to start off by identifying what's the treatment and what's the response. And let's see, it says mothers who have autistic tendencies themselves, so their heredity, are both more likely to have autistic kids. So we're saying heredity can lead to autistic kids, and heredity also could influence you being an older mom. They're saying they're more likely to be older when they give birth. So this right here would be an example of a confounder. It's a third factor, your heredity, that could be causing the response and also is related to the treatment. So I'm going to go ahead and say this one is the confounder. It's not saying, so the causal link would be the first arrow going the opposite way. It's not saying if you're an old mom, you're more likely to have heredity that would make you have an autistic kid. No, they're saying if you already have that heredity, you're more likely to be an older mom. Let's do the next one. So I'm going to do the same kind of diagram. Let's see, we have an older mom. The thing, which in this case is damaged DNA. And then same response, which is autistic kids. This one says as people age, so you're an old mom, as you age, you're more likely, your DNA deteriorates. So if you're an older mom, you're more likely to have damaged DNA, right? They're not saying if you have damaged DNA, you're going to be older. They're saying, no, if you are older, you're more likely to have damaged DNA. And it says this makes them more likely to have babies with birth defects, including autism. So it's saying that damaged DNA is what could lead to having a kid with autism. So this one is the causal link. It's saying, what about the treatment? What about being an older mom could cause the response? Well, if you're older, your DNA is damaged because as people age, their DNA deteriorates. So that's what this one's saying. So hopefully you can see the difference between the confounder and causal link. I know that can be tricky, but kind of think about which one happened first. And you get older, then you're more likely to have damaged DNA, and then that could lead to the autistic kids. The very last one, let's see, it says poor diet, poor nutrition can damage neurological development. So again, we can make our diagram. We have our treatment and our thing that we're looking at, which is poor diet, and then our response, which again is the same, autistic kids. And this is saying poor nutrition can damage neurological development, so maybe it's saying that could lead to having an autistic kid, but it doesn't mention anything about age, so I'm going to say this one is neither. So hopefully the example in the final is pretty straightforward. Somebody asked, what chapters are confounder and causal link from? So this question is based on chapter 2. Chapters 1 and 2 were experimental design. So that was the very first thing that we did in class. So yeah, I always like the first couple chapters because this comes up so often just in life. I feel like I always see, almost every day I see an article that is basically claiming causation when really there's just correlation. So hopefully you guys can take that away from this class. Correlation does not imply causation. All right, if there are no other questions, I'm gonna keep going. It looks like this is more experimental design. So this one says, a study was done to test the effectiveness of an allergy medicine designed to reduce allergic reactions to dust. We had 1,000 adult volunteers. Half were, this sounds good, randomly injected with the medicine, and half with salt water. A week later, the subjects were all exposed to the same level of dust. Their allergic reactions were measured. And then here is the outcome. Oh no, this isn't the outcome. Neither the subjects nor those who evaluated them knew who was in each group. This is telling us it was double blind. This is the outcome. Those who received the medicine had significantly milder allergic reactions than those who received the salt water. So the salt water in this case is the placebo, right? It's just something to not allow the subjects to know which group they're in. So this is good. This is a randomized controlled double-blind experiment, right? This is D. So this is our ideal experimental design. Which of the following statements is best? So we did the ideal experimental design, so we saw that the medicine seemed to work, so I would trust it in this case. It was double blind. There's placebo, there were 1,000 adults, it's a pretty good sample size. So I'm gonna say A, right? This study is very strong evidence that the medicine reduces allergic reactions to dust. This would be the answer if it was a observational study, but we don't have an observational study here, so A looks good. And then 20 says, which of the following are likely to confound the results? So the nice thing about randomized experiments is that they don't have any confounders. So I'm not even going to bother trying to draw my diagrams or waste my time doing this, because the random assignment should make the groups as alike as possible. There shouldn't be any major confounders with 1,000 people. Okay. Any last questions on experimental design? Somebody said, is the final going to be in order like the study guide? It's going to be similar to this, where exam 1 materials first, hypothesis testing's last. All right, I don't see any questions popping up. So next part, more exam 1 stuff. This looks like the normal curve just because I see this right away, normally distributed. So we will go ahead and look at what we're working with. We have mothers' ages normally distributed, average and SD are given, and 21 says what % of the students have mothers younger than 40. So because the data is normally distributed, I can use the normal curve as an approximate histogram here. And I know my data is going to look roughly like that when I graph it. And I want to mark 40 on that curve, but 40 is in years, 40 years old, right? And then my normal curve is in z-scores. So I need to convert 40 to a z-score. And our original z-score formula from very first exam was value minus, oops, sorry, not that. I need to erase this, hold on, not EV. Value minus average divided by SD. I was in exam 3 mode, so how do you know which z-score formula to use? If we're not talking about box models or expected value and standard error, you can just use the regular one. This isn't a random variable, this is just saying we have this data, we know the exact average, the exact SD, what % have mothers younger than 40. So my value is 40, my average was 48, and my SD was 5. So I have a negative z-score, which actually makes sense here because 40 is below average. So I end up getting negative 1.6. And let's see. That's not the answer to the question though, right? It says what percentage? So the answer is just the final answer. So negative 1.6, here's negative 1, here's negative 2, is about right here. And I want to know what % of students have mothers younger than 40. So I'm going to shade everything to the left. And to figure this out, I need to go ahead and figure out what the middle area is first. So if I look up 1.6, that'll give me the middle area between positive 1.6 and negative 1.6. So all of you will have access to the normal table, the t-table, and the chi-square table on the final. And I'm just assuming you guys know how to use the table, so if I look this up, it is 89%. But that's not my answer. That is one of the answer choices, but I'm going to cross it off because I don't want to know what % are between two numbers. I want to know what % are less than 40. So to get this green part, I'm just going to take 100 minus my middle area, minus 89, divided by 2. And that gives me 5.5%. So 5.5% of the class has mothers younger than 40. at least in 2012, that was the case. Okay, what mother's age corresponds to the 16th percentile? All right, again, I'm going to use my normal curve. 16th percentile. I'm going to have to figure out where to even mark that. So we know 0, right? We know that right in the middle of the normal curve that this is the 50th percentile. We always know that one. That's the median. So 16th percentile is going to be somewhere over here, right? It's going to have some negative z-score. So my z-score is going to be negative something. And what that means, the 16th percentile, it means that all the area to the left is 16%. So I'm going to go ahead and say that from my z-score and to the left, this is 16%. But the problem is, how do I figure out what the actual age is? I want an age as an answer. And I guess what I could do is figure out my middle area and then figure out my z-score and then just change it to an age. But the middle area here, it's not going to be 16%. That's the percentile. So what we did back in chapter 5 was go ahead and say, to find this middle area, I can do it in a couple different ways, but I like saying how far is your percentile from 50? So how far is 16 from 50? And that would be 16, why can't I do math? 34, right? 34. And then the other half of the middle area has to be 34. So the total middle area is 68%. So that always works. To find the middle area from a percentile, you can say how far is your percentile from 50, and then just double it. So my middle area is 68%. So if I look up 68%, that's actually one we've seen a lot. The z-score I know is 1. So this is -1, this is +1 if there's 68% in the middle. But I don't want to put -1 as my answer. Instead, I want to convert that to a value. So if I look back up in question 21 at the z-score formula, I can rearrange it to solve for value. So value is just the average plus the z-score times the SD. So my average in this case is 48. I know my z-score is -1, and then my SD is 5. So 48 minus 5 is 43. And those were pretty much the 2 normal curve questions that we did a bunch. I guess 23, we did a few like this as well. It says 95% of the students have mothers between blank and blank. So let's do this with me. Okay, so 95% of students have mothers between blank and blank. So I'm going to draw my normal curve. And I want 95% in the middle. So basically, I want to know what are these 2 z-scores where my lines are, such that the middle area is 95%. Right? Because now we're saying what percent of students have mothers between blank and blank. So this one we've seen before. We can just look up 95 on the normal curve because it'll give us the z-score. And let's actually go all the way down just so you guys can see this. So 95% middle area. Ooh, this is an old normal table. Ignore the height, but 95% in the middle is about right here. And the z-score is 2. So what that means is if there's 95% of the data in the middle, that is between -2 and +2. So that's exactly what I need. So I know my 2 z-scores for that question are 2 and -2. Going back, this is -2. Again, why is this giving me all these problems? This is -2, this is +2. And then I just want to convert those to actual values. So I can use the value formula that I used previously. Value is equal to the average, which we said was 48, plus my z-score. I'll do -2 first, times the SD, which is 5. And that gives me, let's see, 48 minus 10, so 38. And then when I do the same thing for +2, I should get 58, so that should be B. And that is the normal curve. All right, it looks like exam 1 is close to done for this final. I guess 2 more questions about histograms. This was, how many pairs of shoes do you own? It looks like histogram A and B were for male and female answers. Which histogram represents the female answers? You can assume females have more shoes than males. If I'm looking at this, it looks like B definitely has a range from 0 to close to 100, whereas histogram A is like 0 to 40. And then 25 says the following 4 numbers in no particular order are the averages and medians. What is the median for histogram A? So here, this is an interesting one. I know that the 2 averages, these have to be the averages, because our survey data only allows you to put in whole numbers. So I know the median has to be a whole number or a 0.5, a number with a 0.5 decimal. So these have to be the 2 medians. And this is asking what's the median for histogram A. So histogram A is for the male, so it's just going to be the smaller one. Has to be 7. Because it did say you can assume, at least in this data set, that females had more shoes on average than males. Cool. The next one, I'm going to skip the next ones. I'm assuming everyone's probably good with this. Correlation coefficient. The stronger the correlation, the closer it is to 1 or -1. Good? Hopefully good. Questions 30 to 32. Ooh, these are interesting. Suppose the scores on a test measuring artistic skills and athletic skills follow the normal curve, but have different correlations in different populations. So it says to consider the 3 populations where the correlation coefficient between artistic scores and athletic skills are given in the table below. Okay, so essentially here we know this data follows the normal curve, and we want to make a prediction. So this is exam 2 material. We're getting into regression using one variable to predict another. And in this case, we're looking at art skills and athletic skills. So for 0, if there's no correlation, that one right off the bat, I know that this 10th percentile doesn't really mean anything because there's no correlation. So I just have to make a random guess for the athletic skills. And we usually want to, or always if the data is normally distributed, we want to guess the 50th percentile because that's exactly average and exactly the median. Okay, so 0, we always, basically if R is 0, we want to always pick the 50th for our prediction. 0.5, I don't have a rule about it, but I know 0.5 is in between 0 and 1. And 1 and -1 are 2 special cases. So if, let's just say we're in the 10th percentile, and I'm going to say if R is 1, then what is our prediction? Just because then we can use that for 0.5. We know 0.5 is in between 0 and 1. So if R is 1, then that means we make a perfect prediction. Perfect prediction. So that means if you're in the 10th percentile for art, we know exactly what percentile you're in for athletic skills, and it's going to be exactly the same because your z-scores would be exactly the same. So 0.5, looking right here, is in between 0 and 1. So I know my percentile has to be between 10 and 50. So it has to be the 26th. That's my only option. And I could, for 0.5, if I wanted to, I could do this the long way like we did in chapter 8. It was chapter 8, where basically I start with the 10th percentile. So I would start with the 10th percentile. I would find the z-score for the 10th percentile. I would multiply that z-score by r to get my second z-score, and then find the predicted percentile. So I could do all that work if I wanted to. That would give me the right answer. But here, I'm going to kind of use what I know about the special cases. And the special cases are 0, -1, and +1. This looks like it's a -1, but there we go. It's really just, I was putting a dot next to it. Okay, we are good. And then for -1, this is another special case. We can make a perfect prediction again, but it's the opposite. So if we're in the 10th percentile for art, we'd be in the 90th percentile for athletic skills. So the percentiles have to add to 100%. And if you want more practice on percentiles, go ahead and check out the homework from chapter 8. Percentiles and regression. There was a chart in that assignment that would be good practice. Any questions on that? All right, moving right along. More regression. This is in a class of 500 students. Here is the data for the midterm and the final. Ooh, this class, the students maybe didn't do so hot on the final. Okay, in the table below, you're given the midterm score of 2 students. Circle the regression estimate for the final. So I'll do this for the first one and then just assume it's the exact same process for the second one. So here I'm going to use the 3-step process. I guess it doesn't really matter which way I do regression. I could use the 3-step process, or I could find the equation of the regression line. But I'm going to go ahead and use the 3-step process here just because I already have a nice chart. So I have the midterm score, which is 60. I'm going to convert that to a z-score. So remember, formula for z-score is value, which in this case is 60, minus the average for the midterm is 80, divided by the SD, which is 10. So that gives me -20/10, so -2. And then if I multiply that by 0.6, I'm going to get my second z-score, which is -1.2. And then I'm going to go ahead and convert that to a final exam score. So I'm going to use, again, that value formula. So value is equal to the average plus z times SD. And I'm doing this for the final. So the final, the average was 70, not so good. Plus the z-score was -1.2. And then the SD for the final was 15. And that looks good. My answer ends up being for this one, math again, I think 52. Double check my math on this, but I think that's the answer. And then 34, you do the exact same process. So that's the 3-step process. That's one way to make predictions. Probably in general, the more common way that people do this is through the equation of the regression line. So 35 says, what's the slope for that equation? And to find the slope is m in my equation, which is y equals mx plus b if it's in slope-intercept form. So the slope is just r times sdy over sdx. And let's see, in this case, my correlation is 0.6. I have to decide which variable is x and which one's y. So remember, y is always what you're predicting. Y is always what you're predicting. So in this case, I'm predicting finals. So finals is going to be my y. So the SD of y would be 15. And then the SD of x would be 10. One question that I get asked a lot is the second variable always y? And the answer is no. Double check with the question, because especially depending on the randomization or what version you have, you might be predicting finals, you might be predicting midterms, so just double check. Um, 36 says the regression equation for predicting, now we're predicting midterms, so now midterm is my y. For finals is, that's my y, they gave me the slope, finals is my x, and the question is what is b? So it says fill in the blank with the y-intercept. And here, I need to plug in something for midterm and final. I already know the slope, so the only point that I have here is the point of averages. So for midterms, the average was 80 equals the slope is 0.4. For finals, the average is 70, and then plus b. And I can go ahead and solve that equation for b. And this ends up being 52. And then let's see, next question, SD of the prediction errors, which is also known as the RMSE, is what? And this is just basically saying, I guess, do you know how to use the formula? Formula is the square root of 1 minus r squared times the SD of y. So in this case, r is still 0.6, and then the SD of y, this depends, again, on what we're predicting. This says we're predicting finals, so this is, wow, this is a lot to keep track of. I guess we go from finals to midterm to finals for y. So the SD of y in this case is 15. And I think I should get 12. Um, 38 says if 2 points were added to everyone's final exam score. So I guess they must have had to curve it. What would happen to r, the correlation coefficient? And remember, the only time r changes is if we just change one person's score, or if we multiply or divide all the scores by a negative number, then r would change signs. But if we do the same thing to everyone's final score, the correlation between final and midterm is not going to change. So I'm going to say this will stay the same. Two more regression questions here too. It says the regression line is the same as the SD line when, so let's think back, what was the SD line? The SD line is basically the line where when we have a perfect correlation, it's the line that goes through all of the points. So the SD line assumes r is 1. So if the correlation is 1, if we have a perfect correlation, then the regression line is the SD line. They're the same line. This would also work if one of the answers said the correlation is -1. That would be correct as well. 40 says the regression line is a horizontal line through the average of y. So when do we have a regression line that's totally flat? And that's when the correlation is 0. That's when we have just this non-linear pattern of points, something like that. That'd be when r equals 0. If the average and SD of both variables are the same, it depends on what the data is. That doesn't really tell us anything. But any other questions on regression? It looks like the next part is probability. So any regression questions? Regression is chapters 7 through 10, basically. All right, moving right along. These next questions are probability questions. So this was the last part of exam 2 was probability. And here we have a box. This is kind of hard to read. The final is not. This is 0, 1, 1, 2, 1, and 2. So we have a box. It says for 41, 2 tickets are drawn at random with replacement. What's the chance the first is a square? All right, the chance the first one is a square is 2 out of 6, right? And means to multiply. The second is a circle. So it was with replacement, so I'm going to take out the square and put it right back in. So the chance that the second one is a circle is just 4 out of 6. This should be D. Two tickets are drawn at random without replacement. So same question, but now we're taking out one of those squares forever. So what's the chance the first is a square is still 2 out of 6, and the second is a circle. So let's just say I picked the 2, the square 2. Then there's only 5 tickets left, and then 4 of them are circles. So that is B. Next, what's the chance of getting at least one square? So remember, there's 2 special cases, at least one and not all. So this is asking about at least one square, and at least one is complicated. It's easier to look at the complement. 1 minus the probability of none. So I'm actually going to get rid of the ones that don't have the 1 minus, because this is going to make it a lot easier. So 1 minus the probability of getting no square tickets. So the chance of not getting a square ticket would be the chance of getting a circle. So this would be 4 out of 6. Is this with or without replacement? It looks like it's with replacement, so that probability is not going to change. So it looks like A is my answer. So that's the first. The at least one is the first special case. The other one is not all. If we ask for the probability of not getting all of something, remember it's easier to do 1 minus the probability of all. Because not all and at least one are both complicated if we don't look at the complement. We'd have to do multiple calculations. It looks like 44 is an or situation. It says, what's the chance of getting either a square or a 1? So remember, with or means to add. So we're going to figure out what's the probability of getting a square plus the probability of getting a 1. And then with any or situation, we don't want to double count the cards that are both. So I'm going to say minus the probability of both. So the chance of getting a square we've seen is 2 out of 6, plus the chance of getting a 1. Let's see, there's 1, 2, 3 out of 6. Minus, are there any cards that are both? Are there any 1 that are squares? And there is 1. So I'm going to subtract the 1/6. So this is 5, 6, minus 1, 6, 4 out of 6. So with the or situation, just don't forget to subtract that intersection, the probability of both, if it exists. 45 says, what's the chance of getting a 2 if you only draw from the circles? Well, there's only 2 out of 4 circles. So 1 out of 4. And then 46 says, what's the chance of getting a circle if you only draw from the 2's? So there's only 2 2's and one of them is a circle. So this should be 50%. Someone in the chat said, where can we get more questions for practice 21 through 23? 21 through 23. Oh, the normal curve, chapter 5. Chapter 5 and 6. For the normal curve and percentiles. The homework on that, again, or exam 1. So for pretty much all of these questions, you can either redo the homework on Lon Kappa if you want more practice, or you can go ahead and look at those specific questions on the final or those questions from the exam. No problem. All right, a few more probability questions. So this is conditional probability. Hopefully this makes it easier to have the chart here. This says bus drivers are given random drug tests. If they test positive for drugs, they fail the test and face losing their jobs. Suppose only 1% of bus drivers who get tested are really using drugs. If a driver is using drugs, there's a 95% chance they'll correctly fail the test. But there's false positives. 10% of drivers not using drugs will also fail the test. Probably because they're nervous, or maybe it's fluke, or whatever. So we're looking at 10,000 people. It says fill in the 4 missing cells. Okay, so it looks like the total column was already filled in. I usually say fill this in first. And that would be what percent are using drugs or not. And it does say 1% of the drivers are really using drugs. So this 100 came from 1% of 10,000. And then it says if they're using drugs, so there's 100 that are, 95% of the time they'll correctly fail the test. So 95% of these 100 people will correctly fail the test. 5 will pass incorrectly. And then it says 10% of the drivers not using drugs will also fail the test. So we have 9,900 not using drugs, and 10% will fail the test on accident. So this is 990. And then the rest of them, so 9,900 minus 990 is 8910. And now I can answer these questions a lot easier. It says, what fraction of those who fail the test are not drug users? Okay, so we're just looking at this column, the failing of the test. So there's 1,085 people that failed the test, and which fraction are not drug users? So that's 990 out of 1085 should be E. What fraction of those who pass the test are drug users? So now we're looking at this column. 8915 passed, and only 5 of them are drug users. So that should be E. And then these next two questions, I don't think I've said this yet, but we haven't done questions like this. We did do some questions on the law of averages, but it was slightly different than these. So I'm going to say that we can just skip these. This won't be on the final. So if you were confused by those questions, don't worry about them. Okay. Any questions? This is good. We're halfway done. I guess it took me an hour to do the first 50 questions. The final for you guys is 3 hours, but usually we have like 3 students who take the whole 3 hours, so you should finish in about an hour and a half. 100 questions on the final too. Keep going. So the next half of the exam is exam 3 and hypothesis testing. So question 51, it says 100 question true false test awards 1 point for each correct answer and subtracts a point for each incorrect answer. What does the box model look like if they randomly guess on this test? So here, because they're randomly guessing, student guesses, I'm going to say that this scenario, in terms of a box model, is kind of like a gambling game. Right? We had 2 situations with box models, gambling games or surveys. This isn't really a survey. We're only doing 1 student. So for gambling games, you always want to draw the box for 1 play. So I'm going to say draw the box for, in this case, it's not a game, it's a test, so I'm going to say 1 question. So 1 question, it says it's a true-false test. So 1 question has 2 options. There's going to be 2 tickets, and you get a point if you get it correct, and you actually get -1 points if you get it incorrect. So here I'm going to say it has 2 tickets. One is 1 and one is -1. So just beware on this one to not accidentally say there's 100 tickets in the box. Because remember, we want to think about one question and then we're going to draw out of that box 100 times to simulate taking the test and guessing. How many draws do we make? That's where the 100 comes into play. What would we expect the student score to get? Well, this one, I guess if I got 1 point for it being correct and 0 points for it not, I'd expect 50. But this is a little bit different because we get -1 points actually for getting it wrong. So I'm going to go ahead and do the expected value of the sum in this case, because there's no mention of averages or percents, and that is just n times the average of the box. So n is 100, and then the average of this box, let's see, average is 0, right? 1 plus -1 divided by 2. I guess I didn't really need to do this formula, but I get 0. You're expected to get half correct, half incorrect. What is the standard error for the student's score? So in other words, what is the standard error of the sum? Because again, no mention of averages in this case. There's only one student, so we can't really do an average. And there's no mention of percents either. So standard error for the sum is the square root of n times the SD of the box. So I'm going to need to find the SD for this box. So I'm going to do that right here. I can use the shortcut formula because there's only 2 tickets. So I have 1 minus -1, absolute value of a minus b, times the square root of, we have the fraction of tickets marked 1, which is 1/2, times the fraction of tickets marked -1, which is also 1/2. So my SD is 1. I get 2 times 0.5 basically. So square root of 100 times 1 is going to be 10. And 55 says, now suppose you're interested in how many correct answers you'd get by guessing, not the score. Okay, so then the expected value would be 50, right? And it gives us the standard error. It says, suppose a student needs to get 60 questions correct in order to pass. So that's the same case with our final. If you get 60 questions correct, you get a D minus, so you technically pass. What's the probability that this will happen? So I can go ahead, anytime we're asking for probability and they give us a number like 60, that makes me think, it'd be nice to use the normal curve, convert 60 to a z-score, and then shade the area above that, right? What's the chance you get 60 or higher and pass? But this doesn't say that the data follows the normal curve. So the question is that a problem? Can I still do that? And the nice thing is, with random variables, remember we said if we're dealing with sums, averages, or percents, we can go ahead and use the central limit theorem, which says that even if the data itself isn't normal, the sum, average, and percent is going to be. The probability histogram will follow the normal curve. And with 100 questions, that's a big sample size, so we can definitely say that. So I'm going to use the normal curve. It tells me to use the normal curve. I can do this because of the central limit theorem is the name of the thing that says we can do that. And I need to go ahead and convert 60 to a z-score. So z-score formula is usually value minus average divided by SD. But in this case, we are dealing with random variables and expected values. So I'm going to go ahead and use my random variable z-score formula, which is just replacing average and SD with expected value and standard error. So the way you know if you need to use this formula is basically, are you dealing with a box model? Then the answer is yes. If you just have a regular data set, no randomness to it, then you'd use the original z-score formula. And then I'm going to go ahead and figure this out. So I have 60 minus 50 divided by 5. So 10 over 5, which is 2, is the probability of getting more than 60 correct. So I'm going to go ahead and shade that. And then 2, we've seen this C-score before, right? We know the middle area is 95%. 95% in the middle, and then the shaded area is just going to be 100 minus 95 divided by 2. And that gives me 2.5%. This next part says the histograms below in scrambled order depict the sum of 2, 4, and 15 draws from the same box. Match the number of draws to the histogram, and each histogram will only be used once. So histogram 1 is the probability histogram for how many draws. Okay, so I have 2, 4, and 15. I can look at this and say, all right, the number of draws is going to correspond to the number of bars. So the more bars, the more draws. So I'm going to go ahead and say that this one, histogram 1, has the most draws. So this one should be 15. And then the histogram 2 is the probability histogram for how many draws. This is the smallest amount, right? So this should be 2, this one should be 4, and this one should be 15. Histogram 2 is 2, this one is 4. And now, the 3 histograms above represent the sum. Okay, we know that. Which box is it? So the question is, where did these histograms come from? Which box is this coming from? So there's a couple different ways to do this. This is kind of a hard question. I'm going to focus on the 2 draws. So 2 draws, my histogram is histogram 2. So that's right here. And this is, if I look, we have data going from like just above 0 to just above 10. And so I know that if I draw 2 times out of the box, it looks like this is 12. I'm going from basically 2 and 12, I think. So if I draw 2 times out of box A, the smallest sum I can get is 2, right? 2 ones. And the biggest sum I can get is 10. But this histogram, our histogram 2, has values bigger than 10. So I know it can't be box A. Histogram, I guess just looking at box C, same thing. The biggest sum I can get for drawing twice out of it is 10. So I can't actually use that one. It has to be box B in this case, because box B, the biggest sum I could get is 2 6s, which is 12. So that's probably how I would do this. Another way to see all the possibilities is I could say, okay, we're going to draw twice out of box B, which has a 1, a 5, and a 6. And then we're going to draw twice, and then I could see all the possibilities like that. And say I could get 2 1s, which is 2. I could get a 1 and a 5, which is 6, etc. And I can see all the different possibilities. But basically, the biggest sum has to be bigger than 10, and the smallest sum has to be bigger than 0. So I hope that makes sense. But yeah, that's a tricky one. Okay, next part. More polling. It says a recent CNN poll asked a random sample of 900 adults nationwide the following question: would you approve of raising the national debt ceiling at this time? 48% answered yes. Okay, this was from 2012. So it says, which poll better represents the U.S. population's attitude about this? Let's see. We have the CNN poll. It asked a random sample. That was good. And then we had a Fox News poll where anyone could go ahead and vote. And it looks like we got different results. We got 48 and 40%. So remember, the random, just like experimental design, random is always good. So I'm going to go ahead and say B. CNN's better because it used a random sample. Um, 61 says, what is the standard error for the percent of yeses in the Fox poll? So I need to ask myself, the Fox poll was the non-random one, right? It was non-random. So the question is, can I even calculate the standard error? And remember, for one of the reasons that randomization is best for polling and sampling is because then we can use our formulas and calculate things like confidence intervals, margins of error, standard error. So I am going to say, let's just go with D because this one wasn't random. And if I calculated a standard error, it would be biased. And then it says the next questions refer to the CNN poll, which was random. So this one we can calculate a standard error. So it says, what's the standard error? And we got 48% of people saying yes. So to find the standard error, I need to decide, am I dealing with, oh, it says percent, sum, average, or percent. And there's a bunch of percent signs here. So I would go ahead and say it is percent. And the standard error for the percent is the SD over the square root of n times 100%. And the SD in this case, I could use the shortcut formula and say, this is a yes or no poll. So I have the absolute value of 1 minus 0 times the square root of the percent of yeses was 48. The percent of no's would then be 52. Divided by the square root of n, which in this case was 900. And then times 100%. And then that is going to be A. And if I solve this on my calculator, I could go ahead and put this in. I end up getting about 1.67%. That's going to come in handy in the next question. It says a 95% confidence interval for the percent of all American adults who would answer yes to this question is about what? So remember, confidence intervals tell us how, so basically, if we polled all US adults, we're 95% sure that the percent would be in that confidence interval. So a 95% confidence interval is really just taking our sample percent, which was 48%, and turning it into a range. So I'm going to add and subtract 2 standard errors. And I know that I'm going to add and subtract 2 standard errors because the z-score for a 95% confidence interval is 2. So if this was a, I don't know, an 80% confidence interval, I'd need to find the z-score for 80%, and that's how many standard errors I'd add and subtract. So confidence intervals always seem complicated. They seem like you have to do this crazy formula to find them. But really, we're just saying we got this data, 48% in our sample. Let's make that into a range so I can give a better estimate for my full population. It's really hard, you guys probably saw this a lot recently, but it's really hard to have a confidence interval when your percent of yeses is really close to 50%, because then basically you could go below or above, that's included in it. So this is an example of a question where it'd be kind of hard to predict. Basically the American adults could go either way. It could be above 50, it could be below 50. But let's see, so 48% plus 2 times, my standard error was 1.67 if I actually solved question 62. And that ends up giving me, let's see, 48, this should be plus or minus, you can't really see that minus, there we go. This should be, which one is this one? One of these. It's either A or B. I think it's B. Yeah. 64 says a 95% confidence interval for the percent of all American Democrats who would answer yes to this question is about what? So Democrats, this was, our population was adults nationwide, if I look up here, so US adults. So I can't make a confidence interval for Democrats. That could be different, very different from adults nationwide. Any subgroup or larger population, we can't apply this data to. Any questions so far? All right, we'll keep chugging along. USA Today poll asked a nationwide random sample of 1,000 adults. Do you think college athletes should be paid for being on college teams? 24% answered yes. So if I wanted to make this into a box model, this is definitely a survey situation. And in surveys, we always want to draw the box for the population. So in this case, this is a nationwide random sample. There's going to be millions of people in that population. So I know my answer is either going to be C or D, but the question is, which one is it? So we got 24% in our sample. The whole population, that's what we're trying to estimate. We don't know the exact percent. So whichever one of these says basically the exact percent is unknown, which it looks like is D. C is too definite. It says there's exactly 24% marked 1. Well, what we're trying to simulate is we have this big population, we randomly sample out of it. We got 24%. We're going to use that as an estimate for the whole population, but we can't say for sure that's 100% exactly what it is. It should be really close though, because we did a random sample. And then which of the following statements is true? So the expected value for the percent of, are we looking at college athletes, US adults, or US college students in this case? We're looking at US adults, right? This should be B. Is it possible to compute a 95% confidence interval for all US adults? So I'd ask myself 2 questions here. Was this a random sample? Which, yes, it was. And are we looking at the right population? US adults, yes. So my answer here is going to be yes. Sure, why not? And to figure it out, I'd have to figure out what it is. But basically, I could go ahead and calculate it. So I would say I'm going to create a 95% confidence interval for the 24% that I got. I want to make that into a confidence interval. So I know I'm going to add and subtract 2 standard errors. Because again, 95% corresponds to a z-score of 2. And to do that, I need to calculate the standard error. But to be honest, that is probably going to take a while, so I'm just going to tell you guys this should be B. To find the standard error, we can just use the standard error for the percent formula, which is SD over square root of n times 100. Kind of exactly like we did up here in question 61. Or sorry, it wasn't 61, it was 62. Just like we do the same thing. So that's how you do that. All right, 68 says if the sample size was multiplied by 4, what would happen to the standard error? So as our sample size increases, our error should decrease. So I know it's going to get smaller. I'm going to get rid of these multiplied ones. The more people, the less error. More people is a good thing. And if it's increased, if our sample size goes up by a factor of 4, all of our standard error formulas have the square root of n in them. So the standard error is going to go down by a factor of 2. So this is basically, we called this the law of averages. It says as n goes up, what happens to your standard error? And it's different for sums versus averages or percents. Last question before we get to hypothesis testing. 69 says a researcher wants to conduct a pre-election poll. He polled 1,000 people in Maine to estimate the percent who favor Obama over Romney, again, 2012. Now he wants to conduct the same poll in California. Population is way bigger, but we do want the same level of accuracy. So I am going to poll the exact same amount of people, because the same accuracy means you want the same standard error. So we want our ends to be the same. If I wanted to be more accurate in California, I'd need to poll more people. If for whatever reason I wanted to be less accurate, I'd need to poll less people. Someone said, so you know you can compute a CI when it's random. Yes, you can use any of the formulas from exam 3, so expected value, standard error, confidence interval, etc., if you have a random sample, because otherwise we're using those formulas and our data is going to be biased, so they're not going to be accurate. So those formulas all have the assumption that you did a nice random sample. And then I'll pause here for just a sec. Any more questions on exam 3 stuff? Because then we're going to go to hypothesis testing. I don't think there's any other questions. So the next 30 questions are going to be all about hypothesis testing, which we haven't had any exams on, but this will be a good representation of all 5 of the hypothesis tests that we've done. So let's start with this one. A mother thinks her 2-year-old child is particularly gifted in statistics. So to test her claim, I gave the student a 64, or the kid, the child, a 64 question true false exam about statistics, and the child answered 39 out of 64 correct. So the null is the dull, boring hypothesis that says the child is just guessing. 70 says which of the following accurately describes the null box. So again, here with box models, we want to ask ourselves, is this like a gambling game or is it more like a survey? And it's just one child and the null is that they're guessing. So I'm going to say this is more like a gambling game. And in this case, for the gambling game, I want to ask myself, okay, what is one play or one question? That's what I want to draw the box for, one question. So one question, it's a true or false test. So there's only going to be 2 options, 2 tickets. And we're just counting, did she get it right? We'd count that as yes, 1, or did she get it wrong? 0. So this should be a C. So again, I feel like this question about the box models, a lot of times people get confused, especially with something like this. They'll be like, well, are there 64 tickets? What's going on? But just remember these 2 things. Remember, if your situation is like a gambling game, you want to draw the box for one play. And if your situation's like a survey, you want to draw the box for the whole population. And that should help. These draws are going to be made with replacement, right? Because if you get the question right on the first question, you can get it right again. So gambling games are always with replacement. Surveys are always without replacement. And then next, assuming the null to be true, what is the expected value and standard error? So with this one, I could use the formulas. I could use the expected value and standard error for, in this case, I'm dealing with sums. So I could find the expected value for the sum and the standard error for the sum using the formula. But for the expected value, I don't really need a formula because I'd expect under the null, if they're guessing, they just get half of the questions correct. So that would be 32, right? I could use the formula too, but I don't need to. Fill in the second blank with the correct standard error. So that is the square root of n times the SD of the box. So n is 64. That's our sample size or our number of questions. And then the SD of this box is going to be 0.5 because it's just a 1, 0 box with half ones, half zeros. So 8 times 0.5 is 4. All right, so I did all this. Now the question is this child likely to be guessing or not? So I need to calculate the test statistic Z. So I basically need to put this 39 in terms of a z-score to see how far away it is from our expected value. So my z-score formula, again, is going to be value minus expected value divided by standard error, because again, I'm using box models, so I know I want to use that z-score formula. And my value is 39. My expected value is 32 from question 72. And then my standard error is 4. So I have 7 over 4. Oh, I guess it wants, it would be this one, right? 7 over, we're dealing with the standard error for the sum. And I know that because there's no mention of averages and no mention of percents. This ends up being 1.75. This is going to come in handy for the p-value. So to find the p-value, I'm going to use the normal curve. And again, I can use the normal curve here because of the central limit theorem. I'm dealing with sums. So I'm going to draw my normal curve. And I have 1.75. And I want to know what's the probability that the child would get that answer or an even higher answer just by guessing. So the p-value is always going to be the tail. And to go ahead and find that, I'd need to find the middle area between negative 1.75 and positive 1.75. And that ends up being 92% if I look it up. So my tail is going to be 100 minus 92 divided by 2. So my p-value is 4%. It is less than 5. Our cutoff is 5% in this class. And generally in life, that's what they use most of the time. So I would say, if it asked for my conclusion, I would say we would reject the null. The probability of getting 39 answers just by guessing is only 4%. So we're going to say it probably wasn't guessing. Maybe there is a 2-year-old who is gifted in statistics. This is a made-up question, though. Most of these questions are not, but this one is. So this question I didn't even say, this was the one sample Z test, right? We calculated our test statistic, which was Z, and there was only one sample, one kid. So there's going to be on the final one question for one series of questions for each hypothesis test. So here was the one sample Z test. Test number 1, done. Any questions on that? So this is the most basic type of hypothesis test. All right, last August, it says Gallup asked a nationwide random sample of 800 white adults and 400 black adults the following question: do you think that relations between blacks and whites will always be a problem for the United States? Okay, so we got 2 different responses, 55% and 45%. And it says the null hypothesis is that the difference is just due to chance. So here I have 2 different samples. So right away I'm going to say this is the 2 sample Z test. So here's another one of our hypothesis tests. And it says which accurately describes the null boxes. So again, you can ask yourself, are we dealing with a survey in this case or a gambling game? And this one is definitely more like a survey, right? It actually says a nationwide random sample. This was a poll. Gallup is a polling organization. So with surveys, you always want to draw the box for the whole population. And we want to know what are the null boxes, so we want to assume the null is true. I guess I should say assuming the null is true. So in this case, for the two sample z-test, there's going to be two boxes. They're each going to have millions of tickets because we're talking about adults nationwide, and specifically Black adults nationwide and white adults nationwide. So definitely millions in those populations. So I'm going to get rid of this one. And then the question is B or C, which one is right? And remember, for the null box, we want to assume the null is true. And the null, if we look back, right here, it says the null hypothesis is that the difference is due to chance. So the null says there's no difference between these two groups. So I'm going to go ahead and say my answer should be B. And actually this, I'll tell you guys, this is usually the most commonly missed question on the final, because people think that the answer is C. They're like, oh, well, we got 55% in one sample and 44% in the other sample. True, that's what we got in our samples, but our null is that the two groups are the same. And we're trying to figure out, is that difference between 55 and 44 due to chance, or is it actually due to a difference in the populations? So that's what we're going to figure out. So null hypothesis, remember, is the dull, boring one that says there's no difference at all. And for surveys, we always draw without replacement. We don't want to sample the same person twice. And then, okay, they gave us the two standard errors. We have 2.5 and 1.75. So it says, what's the standard error for the difference? So the standard error for the difference, if you remember from chapter 22, it is just the square root of the first standard error squared. So 2.5 squared plus 1.75 squared. And this should be 3.05. So with this one, you want to make sure you have your calculator to do these calculations. To find our test statistic Z, so now the next step, now that I've done all that, I want to figure out how big of a difference is this. So to find our test statistic Z, now I'm doing the two sample z-test, so I have two of everything. So I'm going to say I have the observed difference, so the difference in the two values, so kind of like value minus expected value, minus the expected difference, over the standard error for the difference. So my observed difference in this case was 55 and 44, so 55 minus 44. My expected difference is always 0 under the null hypothesis, and then my standard error for the difference was 3.05. And this gives me 3.6 as my z-score, so D again. Also, sometimes people like to ask, does it matter if you do 44 minus 55 or 55 minus 44? And it really doesn't. You'll get the same p-value either way. I guess you'd get negative 3.6 if you did it the opposite way, but in this case, it doesn't matter which one you use. So it says, assume the p-value is tiny. What do you conclude? In this case, my p-value is definitely less than 5%. It's even less than 0.1%. So I'm going to say my p-value is less than 5%, so I reject the null. So what am I rejecting? If I look back up here, the null is that the difference is due to chance. I'm rejecting that. I'm saying there is a drastic difference between these two populations for this question. There's overwhelming evidence for that. Any questions on the two sample z-test? All right. Let's see what we have next. Right away, looking at this, I see some sort of chi-square test going on here. Let's figure out which one. It says, suppose the instructor of a large class claims to grade on a curve. These are the percentages that they use. Let's go ahead and test the null hypothesis that our observed data fits the percentages. So we're gonna see if this is the case. With this one, I would go ahead and fill out the chart. And what I have here is one variable, their grade, with 4 categories. So I know that this is going to be the chi-square test for goodness of fit because I only have one variable. If I had 2 variables, like if I was looking at grade and what else would I want? What's another category? Like grade and whether or not you're online or in person, then we'd have the chi-square test for independence. But here, just one variable, multiple categories is the chi-square test for goodness of fit. So number 3 for our hypothesis test. And with this one, I would just fill out the chart right away, and then answering the questions is going to be really easy. So for the expected values, we always want to fill these out based on the null. So the null is that whatever the instructor claims is true. So we have 50 students, so 20% of 50 is 10. 40% of 50 is 20. 30% is 15, and then 10% is 5. And then this column is sort of filled in. I'm just missing for C's, so I have observed minus expected. This is 5. I could have, even if I didn't get the expected values, I would know this because this column, the observed minus expected column, should always sum to 0. And then I'm going to square all these, so I have 25, 0, 25, and 0. The question is, can I go straight from this sum of 50 to the chi-square statistic? And because all of my expected values are different, I actually can't. I have to go ahead and fill these in. So let's see, this one would be 0, right? I have this column divided by the expected. This would be 25 over 15, and this one would be 0 as well. And if I calculate this, I end up getting 4.167. So this is chi-square. This is my test statistic. So we use this chart to help us find the test statistic. Okay, and now I can answer all these questions super quickly. So the 4 expecteds are 10, 20, 15, and 5, so that should be A. The value for C is missing in the observed minus expected column. We filled that in as 5. Test statistic is 4.17, about. Degrees of freedom for the chi-square test is always going to be number of categories minus 1. So number of categories in this case is 4, so this should be 3. What's the p-value? Let's go ahead and look it up. So I need to use the chi-square table. So I'm going to go down to, here's my chi-square table. I had 3 degrees of freedom, and my chi-square was 4.17. So I'm going to look, let's see, it looks like 4.17 would be in between these two, right? Here is 4.17. So the p-value is in between 10% and 30%. Let's see if that's an answer. It should be between 10% and 30%. So that should be D. So we've done 3 hypothesis tests. We have 2 more. We have the chi-square test for independence and the t-test. And like I said, there's 1 section on each test. So for this next one, it says the table below shows the survey responses for males and females. What is your opinion of the Occupy Wall Street demonstration? So here right away, I know that this has to be the chi-square test for independence without even reading it, just because it's definitely not the t-test, because look how many expected values or observed values we have. We have 6. And I have 2 variables. I have 2 variables each with 2 or more categories. And if I keep reading, Um, it says, which significance test will be used to test the null hypothesis that the Stat 100 students' opinions are independent of whether they're male or female? So that's my other clue that I'm going to do the chi-square test for independence. Oops. This is what I wanted. Chi-square test for independence. Number 4. Somebody asked, is the final worth 20% of your grade? It's 25%, so it's slightly more than the exams, just because it's a little longer. Okay. 88 says to compute the chi-square test statistic, we need to calculate basically this long formula using the observed and expected values. Should we use the percentages or frequencies? Always use the frequencies for the chi-square test. Any chi-square test, always use the frequencies. What are the degrees of freedom? So again, we're going to do kind of like we did up here. We said number of categories minus 1, but I'm going to do it for both variables. So my first variable is just, are you male or female? So that is going to be 2 minus 1. There's favor, oppose, unsure, or never heard of them. Oops, so this should be 4 minus 1, right? 1 times 4, or 1 times 3. Wow. What is this? 1 times 3. This should be 3. Oops. Sorry, guys. There we go. Right? That looks good. All right. Moving right along. Assuming the null is true, what's the expected number of males who would answer never heard of them? So let's see. Male, never heard of them. We observed. These are our table of observed values. 66. What would we expect? And here what I would do is go ahead and use the shortcut way to do this. There's 2 ways to figure out the expected values for the independence test. And the easiest way, I think, is just by taking the row total times the column total divided by the overall total. So this is part of chapter 23, part 2. But my row total is, let's see, 246 times my column total is 289 divided by the overall total is 717. Right? Row total times column total divided by overall total. So this is, did I do this right? Yeah. B again. And then we could do that for every single category. We could do it for males who said favor, females who said unsure. But on the final, I don't want to make you guys do this over and over again. So we'll just ask 1, maybe 2 of those. And if you can do it for 1 or 2, you can do it for the rest of them. So you'll see here we gave the chi-square test statistic, so you didn't have to calculate it. And the question is, what do we conclude? So chi-square test statistic is almost 40. My degrees of freedom was 3. Let's check the chart really quick. Again, degrees of freedom is 3, and I'm looking for about 40. Wow, the biggest chi-square is 11.34. So 40 is going to have a tiny p-value, less than 1%. So if I go back, I'm going to say my p-value is really small. It's less than 1%. So we're definitely going to reject the null that these 2 are independent. They're probably not. They're probably dependent. So, yeah, A, reject the null. 92 says, if the survey question was changed to a yes or no question, asking, have you heard of the Occupy Wall Street demonstrations, what significant tests should be used? Okay, so if instead of asking, how do you feel about this, we were just asking, have you heard of it? That would just be a yes or no question, right? So we'd have male, female, yes, and no. So 2 categories for each variable. So in that case, if I have 2 variables, each with exactly 2 categories, then I could use the independence test like I just did, or I could use the 2-sample z-test. So that's the one scenario where it doesn't actually matter which test you use out of those two. You get the same results. So kind of like there was a question we did in the notebook about falling in love at first sight. And that was the same situation where you could either do it as a 2-sample z-test or the chi-square test for independence. Okay, we have one more test. We just have the t-test. That's the last one. So I know these last couple questions should be about the t-test. It says, suppose a doctor claims your average body temperature for healthy adults is 98.6, but I think it's less than that. To test the claim, I randomly sample 9 healthy adults. Right away, I'm like, ooh, I have a small sample, and their average is in fact a little bit lower. It says to assume they follow the normal curve. And then what test should I use? So if we're doing the t-test, I guess right away I could say I know this is going to be the t-test because we haven't done it yet. But if I wanted to check, just to be sure, I want to know, are the 3 conditions met? Do we have a small sample? Yes, right? Do we have normally distributed data? I should just say normal data. Normal data. Yep. And then the last condition is that we have an unknown population standard deviation. And in this case, they give a standard deviation, but the question is that from the sample or is that from the population? And this says I randomly sampled 9 adults and that's their SD. So this is from the sample. There's actually no mention of the population SD. So I'm going to say that condition is met as well. So that's how I can double check that this is a t-test. And then because of the t-test, it says if I use the t-test, I'd have to use the SD plus to estimate the SD of the population. So that's the thing with the t-test, is that when we have these small samples, using the SD of those small samples to estimate the SD of the population becomes problematic. So the standard deviation is likely to be too small. We need to increase it a little bit, and that's where the SD plus comes into play. So this formula is just the square root of n over n minus 1 times the SD of the sample. So n in this case is 9, so I have something like this. The SD of the sample was 1. So this is C. Degrees of freedom for the t-test is always just n minus 1, so I'm going to go ahead and do that one right away. N was 9. And then last 2 questions on the t-test. So this one says if I computed 2 test statistics, Z and T, which one is which? So remember, T, I always like to think T is always tinier. And we want to think in terms of absolute value. These are both negative, but I'm going to add in terms of absolute values. Basically, with all of these, the negative versus positive test statistic doesn't really matter. So T is the smaller one, 1.7 versus 1.8. I'm going to say that T is the 1.7. Would the t-test and the z-test both reject the null? Ooh, I'd have to check for both. Okay, so for the t-test, t is negative 1.7. My degrees of freedom was 8. Let's go to the table really quick. Degrees of freedom is 8, and I'm looking for 1.7, which is right in here. So my p-value is between 5 and 10%. So for the t-test, the p-value isn't less than 5%. So I would not reject the null. So T, the answer is no. No for T. I'd have to check for Z. So for Z, I know that the Z statistic is negative 1.8. So to find the p-value for the Z test, I'd have to mark negative 1.8 right here. And then I'd have to go ahead and find this p-value. So the way I would go ahead and do that is by looking up 1.8, finding the middle area, which is, let's see, 1.8 is about 93%. And then this is going to be 100 minus 93 divided by 2. So 100 minus 93 is 7 over 2. This is about 3.5%. So Z would reject, right? Because P is less than 5. P is not less than 5 for T. So we get, depending on which test you do in this case, we actually get different results. So this is kind of to show that it really does, even though the difference between the T and the Z test seems so little, it really does make a difference in terms of our conclusion sometimes. So we want to make sure we do the right one. So here I would say only the Z test would get a p-value less than 5%. That was kind of a hard one too. A lot of work for that one question. And then there's 3 more questions left. These are all about the last chapter, I think, the limitations of significance tests. So the first, question 98 says, suppose a well-designed randomized controlled double-blind experiment is done to test a new drug. Which the null hypothesis is that the drug works no better than a placebo, and a significance test is done and the p-value is exactly 5%. Yikes, sometimes that happens. Which statement best describes what it means? So the p-value, remember, is the probability that we would get our data if the null hypothesis is true. It means that even if the null hypothesis was true and the drug didn't work, we would still see evidence this strong or stronger 5% of the time just by chance. So that is actually pretty much exactly what I said, right? Even if the null hypothesis is true, what's the probability we'd see our data? And that's this. So the other ones, these just aren't true. 5%, there's a 5% chance the null is true. No, there's a 5% chance the null is false. We have proof the drug certainly works. Definitely not. So it's the probability that we would see our data or something even more extreme given that the null hypothesis is true. Okay, number 99 says an experiment on ESP is done 1,000 times. Suppose there's no ESP and the experiment is done correctly with no cheating. Okay, so this is like a mind reading question, I guess. About how many experiments would you expect to find statistically significant evidence for ESP? In other words, how many would get p-values less than 5%? So even if there's nothing weird going on, even if the null hypothesis is true, sometimes in the world we get these strange results that look statistically significant even when they aren't. So these tests, again, have limitations. They're not 100% accurate. So if I did an experiment 1,000 times, basically the 5% cutoff is saying, well, 5% of the time I'll get these really weird results just by chance. So I would say this would happen only 5% of the time. So 5% of 1,000. So 0.05 times 1,000, which is 50. We call that statistically significant. So that's why beware when you do a test multiple times, sometimes you're bound to get strange results, but that only happens 5% of the time. And then the last question. Okay, it says the convention is to reject the null when p is less than 5% and say the results are statistically significant. Is there any mathematical justification for this 5% cutoff? And even though it seems like a lot of people use this 5% cutoff, that there should be a mathematical justification, there's really not. It's just commonly used. It was arbitrary. And it's kind of now just a practice to use the 5% cutoff. People love 95% confidence intervals. The answer should be no. There's no particular justification for choosing 5%. It's just commonly used. Best of luck on your finals next week. I know finals week is super stressful, so I hope that at least the Stat 100 final goes well. It's not going to be very different from the practice exam, so as long as you do at least 2 of those, you should be totally fine. But good luck to you guys. I will be in touch next week about grades and the final. and have a good night.